Okay, so we're on to question 2 from the specimen paper. So let's quickly read the question. The trolley is attached to two identical springs. The trolley is pushed to the left and then released. Figure 3 shows the horizontal forces acting on the trolley just after release. So this image is just after the instant that this trolley has been released. Okay, maybe a bit too dark. Right, so the trolley has a mass of, write down the equation that links acceleration, mass and resultant force. It's one of my favourites. Is it first law, second law or third law? Congratulations, it is second law. So F equals ma. F equals ma. Okay, I don't know why that thing's coming up, it shouldn't be. Right, so that's the equation that links those three things, F equals ma. So once you've been asked to write down the equation, generally they'll ask you to use it. That's one of the little patterns that seems to come up in all the papers. So that's what this looks like now. The trolley has a mass of 0.75 kilograms. Calculate the acceleration of the trolley just after it is released. Give the unit 4 marks. So, because it says give the unit, I can imagine you'll get a mark for the unit. I can imagine that you get a mark for the answer. You get a mark for the rearrangement. That's 3 marks. So there's another mark somewhere. Well, let's have a look at how we'd go about solving the problem. It's not one of the equations you're given, so you have to go from memory, F equals ma. Okay? Then you have to say, okay, what do I know? Well, I know the mass. Oh, I'm working at the acceleration. I've got to rearrange for acceleration. So again, some students might struggle to rearrange this, so I personally would divide both sides by the mass. Cancelling m gives me A equals F over m. You may want to put it into a formula triangle. The two things that are timesing there go on the bottom, m and A. Okay, and then F goes on the top. Cover up A. You're left with F divided by m. Okay, so that's how you'd use a formula triangle to get this. Now sub in the numbers we know. The force. There's 2 forces. Which one shall I use? Well, this is where that extra mark comes in. You've got to resolve the forces. So I've got 1.5 newtons acting in this direction, 2.7 newtons acting in this direction. Right, they're different sizes. I'm actually going to have to, I'll redraw it. It's going to be as though you've only got a force of 2.7 minus 1.5. It's always good to show how you worked it out. Now I can do 2.7 minus 1.5 in my head, although I'm likely to make a mistake. 2.7 minus 1.5. Is it 1.3? 2.7 minus 1.5 is 1.2. See, I made a mistake. So, for 2 reasons, you should be putting this in, 2.7 minus 1.5. 1, it's possible to make a mistake. And 2, you actually can get marks for showing how you work this thing out, even if you make a mistake. 2.7 minus 1.5 is actually 1.2. So 2.7 minus 1.5 is the resultant force on our trolley. This is only 1.2 newtons this way. We've simplified it down. Okay, we've taken this complicated situation here and simplified it to it's an object with 1.2 newtons acting on it, and it has a mass of 0.75 kg. So that's really straightforward. So let's work that out. The mass is 0.75. So now I'm going to do 1.2 divided by 0.75 with the calculator that I brought to the exam because I'm prepared. So the force is 1.2 divided by the mass, which is 0.75, 1.6, whoops, 1.6. Okay, then the units for acceleration is meters per second squared. Don't forget the squared, okay? Right, that should achieve all 4 marks, I hope. Next section. An elastic cord is fixed to the trolley. This shows the arrangement shown from above. So, as before, we had the trolley being pulled this way and pulled this way, and the trolley would have been maybe accelerating this way. So, you've got an elastic cord here now, and it says when the trolley is pushed and released, a wave travels along the cord. So you can imagine if the trolley was in this position here, right? This elastic cord would be up here somewhere, and if it's shot down this way, a ripple could pass down the cord. What type of wave travels along the cord? Right, well, there are fundamentally two different types of wave. There are longitudinal and transverse. Probably spelling them wrong. Longitudinal waves, the oscillations are in the same direction as the movement of the wave, right? So a longitudinal wave might be, for instance, on a spring, squished up a bit, spread out a bit. So you might get a spring and give it a whack like this, and a ripple will travel through the spring, say, for instance, in this direction, and you've got compressions and you've got rarefactions. So compressions and rarefactions, and that is the energy traveling through the medium, and the oscillations are in the same direction as the transfer of the energy. In a transverse wave, the oscillations are at right angles to the transfer of the energy, so it oscillates up and down, and the energy is transferred to the right. So this would be a transverse wave. Transverse, and it would be because the oscillation is at right angles. Oscillation. I have to stop this thing popping up. Oscillation at right angles to wave motion. Right, you better listen to what I'm saying because my handwriting is too hard to read. Suggest one change that could be made to the apparatus shown in figure 4 to produce a wave with a lower frequency. Well, if you've not done the A-level course, this is actually a bit tricky because this setup here, this thing will bounce backwards and forwards, okay? This thing here will just shuttle backwards and forwards, this way then this way, this way then this way. Right, and as it does that, it will send a ripple out like this. Now, there are several things you could do to make the ripple or the wave travelling in this direction have a lower frequency. The easiest one would be finding a way of making the trolley move up and down slower. One way to do that is to have the trolley of a larger mass, okay? And that larger mass means that, as Newton's second law tells us, if you make this very big, then A becomes very small. Okay, so it would move up and down slower, it would move up this way slower, move this way slower, and you'd get less oscillations per second. So the frequency would be less and the wavelength would be larger. So that's probably the simplest thing to do, make the mass larger, or replace the springs with less strong springs. Or finally, you could reduce the tension on the elastic cord, which would mean that the waves travelled slower on the elastic cords and they would arrive further apart in time, also reducing the frequency, and that's what it's asking for, lowering the frequency. Okay, so I think I've covered all the points on that. Let's have a look at the mark scheme and check that I'm doing my job properly. Right, so F equals ma, yes, we got that. 1.6 meters per second squared, I got the right answer. They've shown the, so you've got a mark for resolving the forces. Transverse, the vibration is perpendicular to the direction of energy transfer, yes, I think I've got the mark for that. Finally, use springs with a greater constant. So if you had springs with a greater spring constant, they'd be stiffer. Is that the right way around? Lower frequency. Stiffer springs would produce quicker oscillation. So I actually think there's a mistake in the mark scheme there. Let me check that one more time. Yeah, I think there's a mistake in the mark scheme there. I think stiffer springs would produce faster oscillations. so you would get a higher frequency. So, okay, it is a specimen paper, and there will be mistakes in the specimen paper, and examiners are not always correct. Anyway, hopefully you found this useful. If you have any comments, please make them in the comment section. Thanks for watching.